Hello, students. So, we have a few. What have we done so far? We've talked about limits and continuity of functions. We've shown those two concepts are closely related. We have this other thing called limits of sequences, which has a very similar definition today. And in fact, we've seen that a bunch of limit laws for sequences have direct analogs as limit laws for functions. This suggests that there should be some close relationship between these two things. Today, we prove that there is such a relationship. We're going to come up with a reformulation of all of the stuff we've done in terms of limits of functions and continuity of functions in terms of sequences. So, first things first, let's actually just recall all the definitions because we'll be using all of them today. And if this were an in-person class, this would be time for a pop quiz. So, do this. Take this pop quiz. Give these definitions. Pause the video, do it. Cool, we're back. So, let's state these definitions. For a sequence an and a number L, we say that the limit of an is equal to L if, for every epsilon bigger than 0, there exists a big N, such that for all little n bigger than big N, the absolute value of a sub n minus L is less than epsilon. I say a point is a limit point if, for every delta bigger than 0, there exists an x in the set in question, such that x is different from p, and the absolute value of x minus p is less than delta. For a subset of R and a point P in that set U, so as for a remark, I'll only ask if a point in U is an isolated point of U. If P is not in U, it's not an isolated point. It's just not in U. If there exists a delta bigger than 0, such that for all x in U, either x is equal to P or the absolute value of x minus P is less than delta, maybe I'll draw a picture of that real quick. So there's the number line, and there's P, and there's this radius of delta. There can be nothing in U on either side of P inside of that little open interval. Nothing in U here, except maybe for P. For U, a subset of R, and a function f from U to R, and a limit point P of U, and a number L, we say that the limit as x approaches P of f of x is equal to L if for every epsilon bigger than 0, there exists some positive number delta such that for all x in U, if 0 is less than the absolute value of x minus P is less than delta, then the absolute value of f of x minus L is less than epsilon. And if you left out that 0 is less than, I'm not terribly disappointed, but make sure to remember it next time. That's an easy thing to forget, but it's a very important aspect of the definition. For U, a subset of R, a function f from U to R, a point P in U, we say that f of x is continuous at P if for every epsilon bigger than 0, there exists a delta bigger than 0, such that for all x in U, if the absolute value of x minus P is less than delta, then the absolute value of f of x minus f of P is less than epsilon. We've seen that limits of functions and continuity of functions are closely related. That is, we've proven that if P is a limit point of U, the and came from, I guess at the time I was wanting to use the word accumulation point. Then f is continuous at P if and only if the limit as x approaches P of f of x is equal to f of P. So limits know about continuity, and continuity knows about limits. On the other hand, we've proven that if P is an isolated point, so a point whereat you can't talk about limits, then U is automatically continuous at P. What'll I do today? Well, today is maybe a bad word to say. In this cluster of videos, I will explore the relationship between these two things, which we know are closely related, and limits of sequences. And maybe we'll start with warm-up. This idea of a limit point can probably be detected in terms of sequences. In fact, we'll also do that. What we'll come up with is an alternate definition of a limit point. A limit point is a limit of a sequence of things in the set. But let's read these statements. So here are the things that will be proved. There will be a subsequent reformulation of limit points. Let U be a subset of R and P be an element of R. Then P is a limit point of U if and only if there exists a sequence xn such that for all n, xn is in U different from P and which converges to P. Sequential continuity. Let U be a subset of R. Let f be a function from U to R and P be in U. Then f of x is continuous if and only if for every sequence of elements of U which converges to P, it follows that f of x of n converges to f of P. So, f is continuous if and only if something about sequences. Limits of functions in terms of sequences. Let U be a subset of R, f be a function from U to R, let P be a limit point of U, so I can ask about limit at P, and let's let L be an R. Then the limit of f of x is equal to L, something about limits, is true if and only if something about sequences. For every sequence of elements of U different from P, which converge to P, it follows that f of x sub n converges to L. So let's use these. So my goal in this particular video isn't to prove those. It will be to use those to prove these algebraic limit laws. And here, I'll call the algebraic limit laws. If f of x is a constant function, then the limit of f of x is that constant. If f of x is equal to x, then the limit of f of x is that input p. The limit of f of x plus g of x is the limit of f of x plus the limit of g of x. The limit of f of x minus g of x is the limit of f of x minus the limit of g of x. The limit of f of x times g of x is the limit of f of x multiplied by the limit of g of x. The limit of f of x divided by g of x is the limit of f of x divided by the limit of g of x, provided you don't divide by 0 when you divide by g of x, and provided you don't divide by 0 when you divide by m. Oh, oops. So, what have you done already? You've proven this one already as homework using the epsilon delta definition. In a previous video, I went through a proof of that by doing a full-blown epsilon delta proof. I'm going to say, I already have a bunch of things that involve sequences. Let's use the things we know about sequences. In fact, I'll just prove this claim 6. So, all of the other proofs will be basically the same. Just replace division with multiplication, and you'll get the proof of the one you replace division with the thing you want to do to get the claim you want. So let's assume U is a subset of R. Let's assume that P is a limit point of U, and F and G from U to R are continuous at P. No, I don't want to assume that. I want to assume that they are functions. Let's assume that the limit as x approaches p of f of x is L, the limit approaches as x approaches p of g of x is m, that they both exist, that g of x is never equal to 0, and that the limit of g of x is not equal to 0. So I guess this could also be rewritten as m not equal to 0. Our proof will pass through theorem 3.2.3, which says something about sequences. So let's recall theorem 3.2.3. You should in whatever you're using to read the notes, you should review it. So theorem 3.2.3 says, briefly, the limit as x approaches p of f of x is equal to L is true if and only if for every sequence x sub n of elements of u minus singleton p, if xn converges to p, then f of xn converges to L. So if I want to prove that f over g is continuous, I can instead just check that this condition happens where I replace f with f divided by g. So that means this is the thing that I'm going to try to show. So here's what I'll do. I'll let xn be any sequence of elements of u minus b such that u converges to p. I'll consider any sequence of elements of xn, any sequence xn of elements of u minus p. I'll assume that u converges to p. I need to show we want to show that f of xn divided by g of xn converges to L divided by m. Now, I can also use theorem 3.2.3 on f and g. I know that the limit as n goes to infinity of f of xn should be equal to L, because that should be the same thing as the limit as x approaches p of f of x, which is L. Similarly, the limit as n goes to infinity of g of xn should be the same thing as the limit as x approaches p of g of x, which is m. Oh, wait, but I have a limit law for sequences. That means that the limit as n goes to infinity of f of xn divided by g of xn should be L divided by m. And now let's just summarize. We considered any sequence xn of elements of u minus p, which satisfies that xn converges to p. We showed that the limit as n goes to infinity of f of xn divided by g of xn is L divided by m. So by theorem 3.2.3, so we proved that this holds for f divided by g, but theorem 3.2.3 gives us an if and only if. So if, sorry, I had to sneeze. If the second thing is true, then the first thing should be true. So by theorem 3.2.3, we conclude that the limit as x approaches p of f of x divided by g of x is equal to L divided by m. That completes the proof. To check if you understand this, try to see if you can write down a super similar argument for another of the claims, like how about this one? And in fact, as a homework problem, I will have you compose a proof of this claim, claim 5, using this philosophy of sequences. Cool, so that's where this video will stop. What I'll do in the remaining couple of videos is prove theorem 3.2.1, theorem 3.2.2, and theorem 3.2.3. I'll re-express these ideas that we already have about functions in terms of sequences.